Hello, everyone, and welcome back. In the previous few lectures, we've been talking about functions of a single variable. That is, they take a real number and give you back a real number. Now, 2 lectures ago, we introduced the concept of a limit inside of the function. And in the previous lecture, we talked about what it means for a function to be continuous. Now, through some results, we actually showed that the concept of limits and continuity are very much intertwined. And now that we have a understanding of limits and continuity of functions, in this lecture, we're going to talk about some results that we can derive for continuous functions. That is, knowing what it means for a function to be continuous, what can we say about properties of these functions? Importantly, we are going to prove the intermediate value theorem today, which is a very well-known theorem in calculus. You might be familiar with it. If not, you'll be familiar with it by the end of this lecture. And we're also going to talk about something that you might be less familiar with, but is an extremely important property of functions, and that is uniform continuity. Okay, so let's go ahead. Let's jump right in. The first result that we're going to talk about is, in fact, the preservation of sine. And this is, again, a very, very intuitive thing if you just sort of sketch out a continuous function. But let me give you the result here, and then we can talk about it. So this is just going to be a lemma. It's not really that strong of a result. And you'll see that sort of comes from the fact that the proof is very, very quick and easy. So it's called the preservation of sine. And we say, suppose f is continuous. So it's continuous at a point P. So cont at P. And suppose f of P is positive. Okay, so, at some point, you're continuous and you're positive. Well, then there exists a delta such that if you take x in the domain of f and near P, so in this sort of delta neighborhood of P, that's what P minus delta and P plus delta, that interval means. Well, this implies that f of x is also positive. Okay, so it says if you look close to the point P and f of P is positive, then you're also going to be positive. And of course, you can very, very easily sketch this out. Remember, we think of continuous functions as functions we can draw without lifting our pencil. So maybe we have, something that looks like this. This is my f of x function. Well, maybe I'm looking at, let's say, maybe P is right here, and f of P is clearly positive. Well, then there's a lot of wiggle room just in the picture that I drew, but maybe we'll say this is my delta neighborhood. So this is P minus delta, and this is P plus delta, right? So in this case, there's a lot of choice for delta, but the point of the theorem is, there always exists some delta. It might be super small, it might be 10 to the minus 100, but it still exists. There's always a little wiggle room where your function remains positive. And again, this should be fairly intuitive to you, especially based on my little sketch here. And the best part is the proof is super, super easy. Like it's like 3 lines. Let's check it out. Okay, let's let epsilon equal to f of P divided by 2, which is clearly a positive number. F of P is positive, so half of it is again positive. And so now I have a positive number epsilon. By continuity, of f at P, there exists a delta greater than 0 such that if x is in the domain of f and delta close to P, this implies that f of x minus f of P is less than epsilon. Right, so that's just the definition of continuity. I picked a positive number. In this case, I got to choose what it was going to be because I'm doing something explicit. I'm not showing it holds for all epsilon. I already know it holds for all epsilon. And so therefore, I found my delta. Now watch what happens. If I unravel this a little bit, this gives me epsilon is less than f of x minus f of p, which is less than epsilon. Sorry, the left one is negative, which, let's pull this around. This becomes f of p minus epsilon is less than f of x, which is less than epsilon plus f of p. And now I picked epsilon, so let me put in epsilon here. I get f of p minus f of p over 2, which is less than f of x, which is less than f of p over 2, plus f of p. All right, so all I did is put in my choice of epsilon. But clearly, this gives me f of p over 2. I only took half of it away. I have f of x, and then the right piece doesn't really matter for me. All that I care about is this, because f of p over 2 is positive, which is less than f of x, which implies f of x is positive. And that gives me exactly what I wanted. That's the proof of the lemma, all right? So essentially it says, you can wiggle around really, really close to f of x and still, or sorry, f of p and still stay positive. Okay, so that's just a cute little application of continuity, right? And again, it formalizes, or it makes analytical something that you could probably already draw and probably already intuit just from your sort of basic understanding of continuity, as I can draw the function without ever lifting my pencil. Okay, I promised the intermediate value theorem today, so let me start with a definition. So how is it that we actually talk about the intermediate value theorem from an analytical perspective? Let's look at a definition here. Well, we say a function f has the intermediate value property. Intermediate value property, which I'm going to abbreviate to IVP because that is a lot for me to write every time. On an interval I, if and only if you take any a and b and I, so for all a and b and I, with a smaller than b, we just want to be able to organize these things. And for all k between f of a and f of b, then there exists some c between a and b such that f of c is equal to k. Okay, so a few things. First of all, the definition didn't assume continuity. There are many functions that are not continuous that have the intermediate value property. But what does it say? Pick 2 points in the domain, trace them up to the function, and you say, okay, maybe f of a is equal to 1 and f of b is equal to 2. Then a function has the intermediate value property if you choose any number between 1 and 2, and you can always find a c that's between a and b that gives you that when you evaluate f at c, it gives you that number. So for example, there would be a c that gives me f of c is equal to 1.5 or 1.25 or 1.8, right? Or 1.99, right? All of those would work if we have the intermediate value property. So this sort of naturally leads to the intermediate value theorem. And the intermediate value theorem, so formally says that continuous functions have the intermediate value property. So this is the intermediate value theorem. Now you may be familiar with the intermediate value theorem. Like I said, it's one of these sort of essential introductory calculus results. And it says exactly what I just said, right? Continuous functions have the intermediate value property. So we say, suppose f is continuous on the interval, say, I, then f has the IVP on I, right? So it has the intermediate value property on I. And again, this means, you know, you pick 2 points in the domain, you trace them up to F, and then you can find something anywhere in between it. Take a look at my little sketch of my continuous function here, and you can just pick points in the domain. You can see sort of how this works. Now, one of the main uses of the intermediate value theorem is to prove the existence of roots of a function. Because what it can do is you say you have a function. Okay, now I found, you know, a value A so that F is negative, and I found a value B such that F is positive. Again, the sort of interpretation of being able to draw from F of A to F of B without lifting your pencil, that sort of tells you that you have to go through 0. So this is how a lot of how mathematicians prove that functions have zeros. They use the intermediate value theorem. All you need is continuity. It's really, really easy, right? Continuous functions are everywhere. We use them all the time. And so we're not asking a whole lot of these functions to ask them to be continuous. Now, the best part about this is that the proof uses our, what I'm going to guess is our favorite method of proof, and that's interval halving. So let's check it out. Let's see what this says. So let A and B be an I such that A is less than B, right? So we want to show that the intermediate value property holds in this case. So that means we need to show that if we pick some K between F of A and F of B, then we can find C so that F of C is equal to K. Now, you can do 2 cases. F of A is bigger than F of B, and F of B is bigger than F of K. So we're just going to do one case since the other case is the same. So as a first case, we assume F of A is less than K, which is less than F of B. The case F of B is bigger than F of A is nearly identical. So I'm going to leave that to you to have some fun with. I'm just going to prove the first case where F of A is less than F of B. Okay, so I said we're going to use interval halving. You probably know how to start this, right? The first interval is going to be A to B. So A1 is equal to A and B1 is equal to B. And then let's let M stand for midpoint. This is going to be halfway between A1 plus B1 divided by 2. Now here's the procedure, right? The first piece, if F of M is bigger than K, then let B2 equal to M and A2 equal to A1. And alternatively, so otherwise, let's let A2 equal to M and B2 equal to B1. Okay, so what is it that we're doing, right? We know that F of A is below our K. We know that F of B is above our K. So we look at the midpoint. And if the midpoint, F of M, is still above K, then our new interval is going to be A1 to, or A to M, right? And so what this means is that still the left piece of the interval is underestimating K, and the right end of the interval is overestimating K. So K is still in between. And then the other case is if F of M is below K, then we use the other half of that interval. And we again are still over and underestimating A based on the endpoints of this interval. So then continue this process by having A2, B2 to get A3, B3, and so on. Right, so I'm just kind of being brief here, right, because we know what's going to happen, but that gives intervals, and it's going to be AN, BN, such that F of AN is less than k, which is, well, less than or equal, then less than or equal to f of bn, right? So the left, again, the left side of the interval is underestimating k, the right side of the interval is overestimating k, and you can imagine you're sort of just collapsing down here, right? And because we're interval halving, we've seen this, you know, a million times now, the distance from bn to an is going to 0 as n goes to infinity. That comes from the fact that you're halving the intervals. And so by the nested interval theorem, so that really seems to be a theorem that we're getting a lot of mileage out of, right? Think about how many times we've evoked the nested intervals theorem, even, you know, when we were sort of doing it without evoking it. This is a very, very common proof technique, and it's very, very powerful. So there exists a unique point C that belongs to the intersection of every single one of these intervals, an, bn, and an is converging to C, and bn is converging to C as n goes to infinity. Now, of course, I called this thing C because I know this is going to be the one that gives me f of C is equal to k. But let's see how this works. Well, since f is continuous, it follows that, so we can use the sequential definition of continuity, the limit as n goes to infinity of f of an is equal to f of c, f of c, but also every single f of an is less than or equal to k, so therefore this carries over to the limit, so f of c is less than or equal to k, but also the limit as n goes to infinity of f of bn is equal to f of c. That's just the convergence carrying over into the function because it's continuous. And we know that f of bn is greater than or equal to k, so this carries over to the limit as well. But this tells me f of c is less than or equal to k, so k is less than or equal to f of c, which is less than or equal to k, which therefore implies that f of c is equal to k. And that gives us the intermediate value theorem, right? So just this interval halving technique, over and overestimating the value of k based on the endpoints of an interval, having them sort of collapse down and saying the limit, that's the point you're looking for. So it's a really nice application of the nested intervals theorem. Let's see some examples though. You know, how do we put this into practice? What are the uses of this? Now, I mentioned one of the main uses is proving that there exist zeros of a function. Let me show you another cool application of this. So now we can prove that R, the real numbers, has an nth root of any point P for all n in the natural numbers and p greater than 0. Right? So remember, if you go all the way back to the first lecture, I mentioned I'm not taking nth roots because we haven't proven that nth roots even exist yet. So what I'm going to do is I'm going to prove to you that nth roots exist. And of course, you know, this is right following the intermediate value theorem. So of course, we're going to use the intermediate value theorem to do this. We're going to say let f of x equal to xn, not x squared. And note, of course, we already proved f is a continuous function for all real numbers. All right, so it's in C of R. Remember, we introduced that notation in the last lecture. Also, f of 0 is equal to 0, which is less than p because p is assumed to be positive here. Sorry, let's put this on the next line so it's easy to read. F of 0 is equal to 0, which is less than p. So we've underestimated p here. And then let's also look at f of 1 plus p, which is equal to, of course, 1 plus p to the n, which we can use the binomial theorem. This is 1 to the n plus n times 1 to the n minus 1 times p plus dot, 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 right? So you might have to recall how to do all of this, but it's just the binomial theorem, which, again, we did this technique back in the very, very first lecture. So if you need to refresh, take a look at what we did. But of course, everything here is positive. And so this is bigger than n times p. That is just the second term, right? So I'm adding in a whole bunch of other stuff in here as well. But all I'm doing is selecting out n times p, which, because n is a natural number, this is bigger than or equal to p, right? It's either 1p, 2p, 3p, 4p, 5p. P is positive, so therefore this thing is bigger than p. But this tells me thus f of 0 is less than p, which is less than f of 1 plus p. And so by the intermediate value theorem, IVT in this case, intermediate value property, IVP, intermediate value theorem, IVT. I know it's a lot of short forms, but it's just a lot to write. So we introduce a lot of short forms. There exists some point C between 0 and 1 plus P such that f of C is equal to C to the n, which is equal to P. But that means that we found a number that when you raise it to the nth exponent, or the nth power, it equals p. But by definition, this implies that c is equal to the nth root of p, right? That's just using the definition of the nth root. Now think about how awesome this is, right? Because remember what we had to do to get the square root of 2? We had to like sort of underestimate it and overestimate it. We used the interval halving theorem, or the nested intervals theorem, in order to show the square root of 2 existed. Now, of course, we don't want to have to do that for the square root of 3 or the cubed root of 2 or, you know, all of these infinitely many others. That's just too much work. We don't want to have to do that. So, boom, I just took care of it, all with one example, all with one application of the intermediate value theorem. That's it, right? That is the beauty of the intermediate value theorem. It comes up in really, really strange ways in order to get results about, say, the numbers, the real numbers that you wouldn't have expected, right? Did you expect that you were going to get, we're going to be able to prove that roots of real numbers exist using the intermediate value theorem? This is the cool thing about it. It has all kinds of weird applications. Okay, so that's the intermediate value theorem. Let's talk about another property of continuous functions. As I mentioned at the beginning, this is what's called uniform continuity. So we have a new definition that we're going to use. So we say f is, let's put it in red to highlight it, is uniformly continuous. And this one is very interesting. It says uniformly continuous on a domain D if and only if for all epsilon greater than 0, there exists a delta greater than 0 such that, so we've got epsilon delta notation, such that if you take any 2 points in the domain with or such that they are within delta of each other, this implies that their images under F are within epsilon of each other. Okay, so maybe the first issue that most people have with uniform continuity is being able to disentangle it from just the usual definition of continuity. So what is different here, right? Well, the difference is that if I give you a small number epsilon, you can find a delta so that if you look anywhere in the domain, you find 2 points that are within delta of each other, you can guarantee that their images are within epsilon. If you go back and compare this to the definition of continuity, continuity means that you are focusing around a single point. This says it works everywhere in the domain, right? That's what the uniform continuity means. Uniformly in the domain. Doesn't matter where I look. I can look at any point in the domain. If I look close to that point, the images are close as well. This is a very, very technical definition, and it takes a lot of time to be able to disambiguate it from just usual continuity. But here's the best thing. This theorem right here, very, very famous old theorem. This is a theorem that gave a lot of people, these sort of old school analysts, Weierstrass, Dirichlet, a lot of these big names in 1800s analysis. This is the one that a lot of people focused on for a very, very long time. And it says, if you have a continuous function on a closed interval, right? So C of A, B, that's our notation for a continuous function on the set of continuous functions on closed intervals. Then F is uniformly continuous on this domain. On AB. All right, so that says as long as you're looking at a closed interval, and if I tell you you're continuous on that closed interval, then you have to also be uniformly continuous on it. Now, there's a very, very important piece of this. If that was a half open interval, or if it was just an open interval, this theorem does not hold. There are many, many interesting counterexamples of when this doesn't hold for open or half open intervals. It has to be a closed interval. Okay, that's a very, very important piece of this. But nonetheless, this tells us that, if you were confused about continuity and uniform continuity, well, as long as you're looking at open intervals, you don't have to be confused anymore, because you know that continuity tells you you are uniformly continuous. All right, let's look at the proof here. Well, we're going to assume that this is false and find a contradiction. So we assume the theorem is false to find a contradiction. All right, so we're going to work through this. We're going to see what happens when you assume it's false, and then eventually we're going to get some logical fallacy here. Okay, so that is, we assume F is not uniformly continuous on the interval AB. Okay, so it's a continuous function, but we're assuming that it's not uniformly continuous. Hence, okay, so again, if we think about inverting the logic of these things, if we look at the definition, all of the for every or for alls turn into there exists. All of the there exists turn into for every or for all. So if we just logically negate this, this says there exists an epsilon greater than 0, such that for every delta greater than 0, there exist elements of the domain x1 and x2, such that if those elements are smaller than delta, we have that their images are bigger than or equal to epsilon. So let me write this out. Hence, for all epsilon greater than 0, I messed it up myself. There exists an epsilon greater than 0, such that for all delta greater than 0, there exists x1, x2 in the domain, so in AB, such that x1 minus x2 are less than delta, but f of x1 minus f of x2 is greater than or equal to epsilon. So what I'm going to do is I'm going to take successively smaller values of delta. So let's take delta equal to 1 over n for each natural number. And then by our assumption, by the fact that this is not uniformly continuous, you can find xn and yn in the open interval, in the closed interval, such that xn and yn are within a distance of, this is delta n of each other, so they're within 1 over n of each other, but by assumption, their images are more than a distance of delta apart. So that means you can get a sequence of successively closer and closer elements such that their images are always far apart. And this far is measured by, epsilon. So it could be super small, but nonetheless, it's still far apart. So here's the exciting thing. Xn is a bounded sequence. So since Xn belongs to a closed interval, this implies Xn is bounded, right? It's bounded above by B and it's bounded below by A. So by the Bolzano-Weierstrass theorem, do you remember this one? This tells us that there exists a convergence subsequence. So there exists a subsequence Xn sub k converging to some p in the interval. Okay, sorry, as k goes to infinity. And we'll comment on why we need a closed interval to make this work as we at the end of this, okay? But now, if you look at the same subsequence of yns, so ynk, so the same indices that you picked out from the xn subsequence, you look at the same indices for the yn subsequence. Well, this is using the triangle inequality, the distance from yn to xnk plus the distance from xnk to its limit p. But this thing, let's just put a little blue marker under this. This is less than 1 over n sub k, which is going to 0 as k goes to infinity. We already know this is going to 0 as k goes to infinity. And so therefore, the whole thing is going to 0 as k goes to infinity. So that tells us that, so thus, ynk is also converging to p as k goes to infinity. So the subsequence of yn is also converging. So therefore, since f is continuous at p, right, because it's continuous every point in the interval, then that tells us f of p is equal to the limit as k goes to infinity of f of xnk, and it's also equal to the limit as k goes to infinity of f of ynk. But what does this mean? That is, okay, well, we know epsilon is less than or equal to the distance from f of xnk minus f of ynk. That's by assumption of this thing not being uniformly continuous. But this is by the triangle inequality, xnk minus p plus f of ynk minus p. So I just applied the triangle inequality, added and subtracted. Sorry, that should be f of p, pardon me. Not just p, f of p. It's image, which clearly goes to 0 as k goes to infinity because I just calculated those limits above. But epsilon is positive, right? So I said that the original distance is bigger than 0 for all k, right? It's actually bigger than epsilon. So, epsilon could be 1 over 10 to the 100, but it's still positive. But the right-hand side of this says that I can make that thing as small as I want. In particular, I can make it smaller than epsilon. This is a contradiction. So thus, f is uniformly continuous on AB. I apologize for the short forms, everyone. It's just that, I wanted to squeeze this in at the bottom of the page, not starting a new page, making it confusing. Okay, so let me ask you a question. Pause the video and ask yourself, why is it that I needed a closed interval to make this work? So think about it for a second, pause the video. I'm going to tell you now, though. Where is it in this proof that I needed a closed interval right here. That's where I needed a closed interval. I need to know that P belongs to the interval itself. If I had an open interval, then the limit doesn't necessarily have to stay in the interval. So let me give you an example, right? I can take this sequence, xn is equal to 1 over n, which belongs to the open interval 0, or the half open interval 0 to 1, but xn converges to 0, which does not belong to that interval. So that means that I could have a sequence of elements inside the open interval that converge to something outside of it. The nice thing about closed intervals is that they contain their limits. You can prove this, and we have done this, in particular with the case of least upper bounds, but that's the issue. And that's where things typically go wrong when you have open intervals. So typically, if you want to come up with a case of an example that is continuous on an open interval, but not uniformly continuous, it's because something is going wrong at the endpoints. So an example of this would be the function 1 over x on the open interval 0 to 1. That is not uniformly continuous, and therefore you get an issue at the endpoints. And of course, in that case, the issue is that you've got an asymptote at 0, and so you can't even evaluate the function at 0. So you could have, a sequence, say 1 over n, that's converging to 0, but you cannot evaluate a limit of that thing in terms of, f of xn. Okay, so we had a little bit of fun today. We got to talk about continuous functions. Maybe we got to talk about things that we knew, but now we proved them for the first time. Or maybe we got introduced to some new concepts, such as maybe uniform continuity. So, we got to see how we can use continuity of a function to talk about the preservation of signs, or even, talking about the intermediate value theorem, something that we probably are familiar with from an introductory calculus class. But uniform continuity is certainly potentially a newer concept, and it's one that takes a little bit more time to work with. So again, I want to emphasize the best thing to do is go back and look at the definition of continuity and compare it to the definition of uniform continuity. The difference is continuity is for one point in the domain. Uniform continuity holds for every point in the domain. So you have different deltas for continuity than you do for uniform continuity, same delta for every point in the domain.